So welcome to the sixth lecture. We call it SneakySnake, which is one of the last pre-alignment filters that we are going to explain. We may have one more on Graham filter. And after that, we'll move with different topics with my colleagues. I think we'll have 4 lectures more. And hopefully by that, we cover different aspects of genome analysis, or at least focusing on the hardware acceleration plus new algorithms that develop by us. So as a reminder, remember all the course materials are already public online on YouTube and on the course webpage. You can access using this link. You'll see the slides in both formats, PDF and PPTX. And we will continue now with pre-alignment filter, which we already explained 3 more filters, gatekeeper, magnet, and Shuji. So remember this from the previous 3 lectures, that sequence alignment is still expensive, even until today. So our goal is to accelerate read mapping by reducing the need for dynamic programming algorithms. What does that mean? We first want to have this observation that genomic sequences either similar to each other or dissimilar to each other. And if they are dissimilar, they are probably not interesting to us. It depends on really the applications, the parameters, how you really define similar or dissimilar sequences. As we said multiple times, if your edit distance threshold is 5, and then the number of edits between any 2 sequences is 6 or 7, then that is what we call dissimilar sequence. And in this case, we really don't care about the type or the location of these edits, whether they are substitutions, deletions, or insertion. We just ignore them. If they are similar, we want to find the exact location of each edit operation that we recorded in what we call a cigar string. Cigar string is a representation of the number and the location of these edit operation. If calculating the dissimilar sequences, always expensive. Why? Because we always going to trash whatever computation we did. So it's always better to perform the minimal number of computation needed just to identify whether this is dissimilar or similar. If it's similar, there is no way to escape the computation needed for that, because anyway we need the optimal number of edits, the exact type of edit, and the location of these edits. So the main idea of all these pre-alignment filtering is to do some kind of indexing first, where you can get some seeds or subsequences from the read, and try to match them with the subsequences extracted from the reference genome. And because the reference genome is only one and fixed most of the time, most of the run time, so we normally store them in a hash table or any kind of indexing. Could be Boers-Wheeler transformation or something else. From the read are something as input coming by the user. So every time we run the tool, we probably have different read set. And that's why we don't store them in a hash table. So we just extract seeds from the read, try to query them in the hash table, and then try to find the location that share enough number of seeds. Once we identify these locations that has a pool of seeds around them above a threshold, we can set a threshold, for example, 5 seeds, nearby seeds. If we have 5 nearby or more seeds, then we need to do sequence alignment or dynamic programming algorithm. But as we said, we really want to use the minimal computation at this stage just to identify the dissimilar sequences first, and then we can proceed with the dynamic programming algorithm. And we said, whatever filter you develop, they should satisfy these 3 conditions. First, filter out most of incorrect mapping. And we said why we say most of, but not all of them. If you still remember, maybe you can write in the chat the reason for that, or you can enable the mic. People on YouTube can also participate, write in the chat box why we filter out most of incorrect mappings, but not all of them. Let's wait a bit until we get some answers in the Zoom chat or YouTube. Why we filter out most of incorrect mappings, but not all of them. Going once, get an answer. Filtering out all of them is too expensive. Why it's too expensive? Maybe someone who can develop very smart filtering algorithm that can remove all of them using some cheap computation. Is it possible? Think about sequence alignment. If we use something similar to sequence alignment to do the filtering here, what will happen? Someone develops something very rigorous, very smart, that can detect these dissimilar sequences and delete them. So just keep this question in mind. We have a slide toward the end of the lecture, and that hopefully answer all these questions. All right, thanks, Richard. So the second properties that we need to maintain is preserving all correct mappings. And this is obvious, right? What's the goal of deleting the similar sequences? We will lose the idea behind developing read mapper, right? So we really need to maintain all of them. The third one is do it quickly. Why is that? Because this is the main goal actually behind filtering. So we want to filter the dissimilar so that we have a minimal workload for the sequence line. So the dynamic programming algorithm will be only operating over the similar sequences. So for SneakySnake, we make a key observation based on this plot, which we call it dot plot. This is not proposed by us. This is a very old method to represent similarities between very long sequences. And it was proposed in 1985. What is it actually? This is a table. This is an entire table. This software. My camera is disconnected. Yeah, let me try to solve it quickly. Almost there. Doesn't want. All right, so let's switch to the old camera, the laptop camera. Okay, yeah. So hopefully you still can see the slides.
Yes, we can see the slides.
Great, thanks, Drew. Okay, so what is this dot plot or dot matrix? So basically this is a table, really a table, and each dot represents a single entry or a single cell, single entry in this table. And what we have here in the x-axis is one of the genomes. Each entry represents a location. So this is location 1, for example, 2, 3, 4, 5, 6, 7, 8, until the end. The y-axis is another sequence that we are comparing with. So we are comparing this sequence to that sequence. Whenever we observe an exact match with the corresponding base or character from the other sequence, we represent it as a dot. Now, whether we represent it as a red or blue dot, that's another question. We don't care at this point. But what is important to us is that whenever we have similar sequences, we observe that most of these dots are scattered around the diagonal. So you can see here, this is the main diagonal, and most of the dots are scattered around there so that we have connected lines between these dots. Remember, this is different from dynamic programming. We don't have any dependencies. So this is just like Hamming distance. Whenever we compare, for example, the first character over there with all characters from the other sequence. Whenever we have exact match, just place a dot over there. There's no dependencies at all. Now, we leverage this observation, or we exploit it actually, to do SneakySnake algorithm. So the correct alignment is a sequence of non-overlapping long matches. And these are the non-overlapping long matches, which are the things around the diagonal. So we said, okay, so let's approximate edit distance calculation using what we call single NAT routing problem in VLSI chip. We observe that also in single NAT routing problem is something very similar to connecting these dots or finding these dots or long non-overlapping matches. How is that? So this is the VLSI chip, which exists in any kind of electronics, in your phone, in your laptop, and so on. So if you dissect this chip, you will see something like this. So these are the pins or the legs of this chip, and you'll see some components from inside. The goal as electrical engineer or chip designer, you have some components here, and you want to connect one of these pin to the other pin in the other side while connecting some of these components inside using shortest path. Now, shortest path or lowest cost has multiple definitions. It could be the lowest latency, the minimum energy consumption, or the least routing cost, for example, because these routing path, you pay cost for them, right? And you don't want to increase their number because they're going to increase the energy or taking space because they will collide with those modules. So your goal is to find the shortest path from one point to another point while connecting some of these components or avoiding these components. It depends on your design schema. So that is for single NAT routing problem. Now, how we solve it in reality. So in the paper, in SneakySnake paper, we show the exact equation to build this, what we call chip maze. And this chip maze, we calculate a binary matrix or a binary table using this equation. You can see the equation is very simple. So you just need to track the I and j indices, and then you either solve or fill or calculate the entry as 0 or 1. So for example, here, J and J, it's really the corresponding characters from both sequences. If they are similar to each other, you just place a 0, otherwise a 1. And then you shift one of the sequences, which is Q. You try to get a different indices over there, and you compare it with J from R, and so on. You continue doing that until you calculate everything. Now, how many columns? As long as we have in the sequence. So how many characters we have in any of the sequences, then that is the number for the columns of the chip maze. Now, what is the number of rows? Is 2e plus 1. What is e? Edit distance threshold. So 2e plus 1. And here we define e as 3, then we have 7 rows. So 7 rows times 12 columns. Anyway, assume we have this matrix, this binary matrix. Now, we want to convert it into a VLSI chip. So we want to visualize this as if it is a chip. How is that? So simply convert each one into a black box, each 0 into a white box, as you can see. Just each one, think about it as if it is a module in the VLSI chip. and the 0 as available path, where you can detour or place your routing path over there. Okay, hopefully this is clear. Now, once you have the VLSI chip, your goal is to go from here, from the left side to the right side, by maintaining or preserving the characteristics you have, whether it's the shortest path, the lowest cost, and so on. We define this as the shortest path with minimal number of edits. So we want to go from left side to the right side while maintaining the number of edits or obstacles or modules that we can avoid up to 3, up to E edits. So equal or less than 3. So how we solve it? It's very similar to single net routing problem. In each row, you detect how many steps you can go further. So you find here 0 steps because you start with an obstacle or a module, then you cannot pass. So here you cannot. Here you can move 4 steps forward because your goal is always to go from left to the right. So you want to go as far as possible in each row. That is a greedy choice to get with the shortest path. Because if there is no obstacles at all, then you just walk in a single row and that's it. You solve the problem. Now you continue calculating until you ensure that you find the path with the longest distance or the largest path we have over there, which is the one in the middle. It has 4 steps to walk forward and the others have less than 4. Now, if we have 4 somewhere in another row, that's fine. That is a tie. And how to break the tie? Just choose any one of them. As simple as that. Now, once we move 4 steps forward, we face an obstacle over there. So to move forward and solve another subproblem, we need to reduce the 3 obstacles over there allowed to us by 1. So now we reduce it and becomes only 2. So only we can avoid 2 or less obstacles. And now we repeat the exact same steps, but we start calculating from the next column. We don't start from the column where we stop or where we have the obstacle, but we move to the next column. And we find the rows, this is 0, 0, and this is 4 steps forward, 0, 2, 0, 0. So which one we choose? We always choose with a greedy choice, the one with the largest number of available steps, which is 4. So we choose 4, we face an obstacle over there, and then we reduce the number of obstacles we have from 2 to 1. And now we repeat starting from this column, not that column, not where we stopped, but the next one, as I said. Now we keep calculating each row. And in this case, you can see that we find 3 paths with the exact same number of available steps. So all of them has single step to move forward. Which one we choose? As I said, this is a tie, and to break the tie, we need to choose any one of them. It doesn't really matter. Now, some of you could say, how come it doesn't matter? Because if I choose one far from this path, I'm going to use a vertical path as well, and that is a cost for the silicon or for the metal layer in the VLSI chip, right? So because we have multiple layers stacked on top of each other, to have vertical and horizontal lines or connections, and then soldering these layers far from each other or this connection might give you some cost, right? Because you are going to occupy this entire vertical connection over there. Now, for us, we define the problem that we don't want to find the optimal number of edits, but we want to find something that give you insights about the number of edits. We really don't care if the exact number of edits is 5 or 6 or 7. As we always say, in filtering, we want something to tell us whether the number of edits is above a threshold or lower than a threshold, right? So we don't care if it's 7, 8, 9, and so on. As long as it's above 5, then done. That means these are dissimilar. If we are really interested in finding the exact number of edits, then we are going to use sequence alignment or dynamic programming anyway. So in the next step, we are going to use the dynamic programming. And for that, at this stage, we try to simplify the computation so that we don't have any dependencies at all We don't want to measure the distance from this connection to the next connection, for example, because that's going to cause some problems, especially that you may have something closer to the path, but not with the largest number of steps, for example. Then you need to check the distance first, and then come back and check the vertical distance between these paths. All right. So finally, we find the last path that can send us to the exit while we maintain the number of available steps or obstacles that we can avoid. Since we face an obstacle over there towards the end, we're going to reduce the number of available obstacles from 1 to 0. So since we reach 0 or more steps while we reach the end, then that means these two sequences used to build this table or binary table or chip maze, they are already similar, right? So once we terminate SneakySnake, then if they are similar, we directly call dynamic programming algorithm, which can be Smith-Waterman, Needleman-Wunsch, KSW2, wavefront algorithm, and so on. Now think about when we calculate the first step. We said we have an obstacle over there, right? In the very first row, very first cell, we have an obstacle. So once we face an obstacle, we directly go to the next row and we keep calculating, right? So this is exactly what we need to calculate, not the full matrix, but actually this. So I trick you by saying that we need to use that equation to build the matrix first, but in reality, we build everything on the fly. So while we're moving, we calculate row by row. So we go to that cell, we use our equation to calculate it. If there's an obstacle, we terminate that row directly. And then we move to the next row, and then to the third row, and so on. So thinking about very long sequences, you can see the amount of computation we save by not calculating most of the matrix. So it really depends on the two sequences, but on average, we don't calculate most of the entries over there because there's always a solution if this is similar sequences, and the solution is to find a path. So only that path and some alternatives path will be calculated. Other than that, you will always have an obstacle in the beginning, and then you won't calculate most of it until you find the next checkpoint. These checkpoints, we don't know them in advance either. So we only know the checkpoint 1, but after that, we need really to calculate each row until we got the second checkpoint and so forth. And so you can think about how fast this algorithm can be compared to dynamic programming algorithms, even in C implementation or Python or whatever. So we implement this on GPU, FPGA, and CPU. And these are the results for FPGA resources. So this is the number of lookup tables needed. You can see most of the cases is less than 1 or less than 2% at most. And that is very cheap algorithm to be implemented in FPGAs. And since it's very lightweight with very low footprint or resources footprint, then you can use a lot of or large number of replications. So you can, instead of solving single problem, you can have 50 problems, for example, or 100 problems if the utilization is less than 1%. It really depends on the edit distance threshold. Why is that? Because for 5 edit distance threshold, for example, how many rows you are going to build? Remember, we said there is an equation for the number of rows, right? The number of columns is equivalent to the sequence length. If we have a million long sequences, then we need million columns. But the number of rows depends on the edit distance threshold, which is 2e plus 1. So if we have 5, then we have 11 rows. That is more computation than edit distance threshold of 2, for example. However, since we were using an outdated connection in that time with PCI Express 3, I think we couldn't move many of the data to the FPGA to be processed with a single cycle. So we are able to saturate the memory bandwidth using only 16 modules, but we could fit more if we use more sophisticated connections between the CPU host and the FPGA. These days, we have higher memory bandwidth. You can accommodate the data in the memory and then of the FPGA and then move them to the FPGA or to the logic to do the calculation. And this is what we exploit in the next paper. Now, remember, going back to the question I asked earlier, why we cannot remove all incorrect mapping or all dissimilar sequences. Now, this is a plot that has too many information, so I really need your focus over here. Now, in the x-axis, we have information on the filtering. So the first row, we have the rejection ratio of the filter. So the 100% means the ratio of the rejection. So how many or the portion or the percentage of the input mappings or the pairs get rejected by the filter. So we have 100% all the way to 20%. The second row is the speed of the filtering compared to the sequence alignment. So if the filter is 2x faster than the alignment, or 4x or 8x, and so on. So we have 8x, 16x, 32x, and so on. Now, the green line, or the y-axis first, is the processing time for 1 million mappings. So, for example, at this point, we have 10,000 seconds for 1 million pairs, right? So now assume we have the sequence alignment. We want to process this 10,000 or this 1 million sequences. So we run sequence alignment and assume constant time for whatever the pair is. And then we will take always 10,000 seconds to process these 1 million mappings. Now we want to measure the time for filtering plus alignment, giving that these characteristics are satisfied. For example, if we say 100%, then 100% of the pairs are rejected. So this is what we get. Really a zigzag shape plot. What does it say? So focus at this point, for example. Now, if the filter rejects everything, totally everything, so 1 million pairs get rejected, what does that mean? It means we have 0 time for the alignment because there is nothing coming out of the filter. And the only time we will calculate over here is the filtering. So the filtering time will be accounted for because the only thing operating is the filter. And the filter is 2x faster than the alignment. So that's why the runtime over here is around 5,000 seconds, which is half of the alignment. Now, as long as we reduce the rejection rate, the filtering time starts to dominate and even being slower than sequence alignment alone. So if we reject only 20% of the pairs over here in the peak, only 20% get rejected, and 80% of the pairs go to the alignment, then what will be the execution time, the total execution time? So again, we will have the execution time for the filtering for the entire number of pairs or the entire data set, which is 1 million pair. And remember, the filter is 2x faster than the aligner. And then we need 5,000 seconds just for filtering, plus whatever the execution time for the aligner for the 80% of the pairs. And this way, we are increasing the execution time because we add an overhead for the filtering and we reject only a minimal number of pairs. Likewise, you can think about it exactly the same for other data sets or other conditions. For example, here, we delete 100% of the pairs and the filter is 16 times faster, then the execution time will drop from here, from the 10,000 seconds, all the way to maybe, I don't know, 200 seconds, around 500 maybe, right? And that will be the execution time. So the speed up we expected from integrating pre-alignment filtering with alignment really depends on the data itself and how fast the filter is. Our goal is always to be in this area. to be as far as possible from the execution time of the aligner or the sequence aligner we use, right? So we want always to be in this area. That is to say, we want to reject most of the pairs and have the fastest performance possible out of the filter. Now back to the question, why we cannot reject all incorrect mappings. Think about the optimality. So if we really have such optimal algorithm, like this algorithm is very smart, can know all the incorrect mappings, then there's no way to be a filter that should be a sequence aligner. If an algorithm can reject all dissimilar sequences, it means the algorithm is optimal, right? It might not be optimal in finding the location of the edits or the number of edits, but at least should be optimal in detecting these number of edits above a threshold or lower than a threshold and should guess it right. And in such optimal algorithm, it's hard to believe that you have an optimal algorithm that performs faster than the sequence aligner. That is in general case. You may focus on special cases where you have, for example, some of the scoring or some of the parameters. You can focus on them and tweak the algorithm for these scores, and then you might get a faster performance than a typical or general purpose sequence aligner. But still, if you get an optimal performance, then what is the point of using filtering if you can have such optimal algorithm to detect the dissimilar sequences? So that's why we don't aim to do filtering for all incorrect mappings, but we want the largest portion of the rejection rate. That's why this gray area, the shade over here, it's not touching the 100%, because this is really ideal case or the optimal, very optimistic case. But we aim to have something like 90% or so, something around that. Hopefully by that, I give you a clear idea on the benefits of pre-alignment filtering. So getting information on the filter itself is not enough. You really need to check the number of accepted pairs and then compare the runtime of the filter with the sequence aligner and see how both together, integrated together, perform. So pre-alignment saves more than 40% to 80% of the total processing times. Of course, that depends on the data you use. All right, so given that you already see Gatekeeper, Shuji, Magnet, and now SneakySnake, so you can get a clear idea on the accuracy, hopefully. So in SneakySnake, we don't have any dependencies. We don't have a domination with the zeros as we have in Gatekeeper and Magnet as well. So you can see SneakySnake performs the best, even better than Magnet. So you can see the black plot over there. This is SneakySnake, and the green one is Magnet, the light green. The dark green over here is SSD, then Gatekeeper overlaps with that. You can see, for example, Gatekeeper at a distance threshold 9 or 10, they don't reject anything. So they accept basically everything. So they have false accept rate of 100%. And Shuji somewhere in the middle. But they still all performs very well up to 5%, which is the typical used at a distant threshold. So we normally use somewhere around 5% of the sequence length. Okay, so back to the previous slide where we motivate you to always measure the runtime end-to-end, filtering plus alignment together. We did this experiment with one of the fastest or one of the best optimal sequence aligner that does not sacrifice anything called Parasale. And there is no heuristics, for example, used over there. And that's why it's really expensive algorithm. In the yellow plots or yellow columns, you will see the performance or the execution time of SneakySnake only, the filtering. And in the gray columns, you will see Parasale, just running SneakySnake alone and run Parasale alone, you'll get these plots. And now, if you go to SneakySnake, you get the accepted pairs and you try to run parallel on only the accepted pairs, you'll turn on. How about now? Can you hear me? Yeah, I think yes. The headset turned on, so the voice transferred to the other device. All right. So yeah, as I said, the yellow is SneakySnake only. The gray is parallel, and the green is parallel operating over the accepted pairs by SneakySnake. And you can see it depends on the data, but it looks like most of the data having edits more than 700. Because here parallel barely operate on anything, but after that you start to see some execution time for parallel after SneakySnake, which are the green bars. It means there are some pairs accepted by SneakySnake. That's why we see some execution time. And you can see the speed up, we observe it all the way up to 1,250 of edit distance threshold. And when we use, this is for 10,000 long sequences, and this is for 100,000 long sequences. You can see in the 100K, the speed up is observed up to 11,000 of edit distance threshold. And these edit distance threshold really high, especially for hi-fi reads, for example, which are very accurate. Even for ONT, this threshold is really high, set really high, because recently the error threshold or the edit distance threshold should be somewhere between 2% to 5%, especially with the R10 chemistry we have in nanopore devices. That is for parallel. Now, if we move to the fastest alternative, which is KSW2, to use a lot of heuristics, for example, Z-drop, and many more with SIMD vectorization and so on. So we can see the speed up is somewhere around the same ratios, but the speed up ratio itself is less than what we observe from parallel, because now the sequence aligner is faster than parallel, but SneakySnake still the same performance. So you can see here we have a huge speed up when most of the things get rejected by the filter. So you can see at the distance threshold 1, most of the pairs are rejected, and that is around 100% of them. Now, if we move to 31, we may have some pairs accepted and so on. You can track it with the red plot. You can see when we have rejection or acceptance, actually. So at here, we have 10% of the pairs get accepted. And here, 50% or 45%, all the way to 90%. So we observe whenever we accept up to 70%, which is really high, if we accept 70% of the pairs, that's really something high. And then we observe almost the same performance as KSW2. So it really depends on what kind of filtering or what kind of indexing you used before, how many seeds you extracted, and so on. All of these will play with the number of edits you have in the pairs, especially in the read mapper. If you extract a lot of seeds from the read, then that's going to let you suffer by querying the hash table multiple times, and always accessing the index can be expensive because it cannot fit in the cache. So you need to go to the main memory most of the time, get the query, or does it exist, does not exist, and come back to the CPU, and then start the processing. So either you want to suffer during the indexing or during the filtering. That is your choice. Hopefully by that we cover most of the things about SneakySnake. We observe up to 4 orders of magnitude more accuracy than Shuji and Gatekeeper. And then we accelerate IDLib, which is one of the best or the best performing implementation of Meyer's bit vector. They have a lot of configurations for local, G-local, and global alignment. And they have also 2 configuration for the path and without path, that is to say with generating the cigar and without generating the cigar. But IDLib is calculating only edit distance at the end, or Levenstein distance. For paracels, do the full sequence aligner. And these are the speed up numbers using, as I said, we implemented on FPGA, GPUs, and CPUs. However, since we use all these accelerators, we need still to move the data from the host CPU or the host memory all the way to the FPGA or the GPU. So we need to move the data from there to the memory of these cards, and then we start processing. And we really need to alleviate data movement bottleneck. We know that data movement is always expensive because they use power-hungry buses over PCI Express, for example, or something else. That will cost you a lot in terms of energy. You could overlap the data transfer time by doing a lot of computation while you are transferring the data, but that's still not solving the issue with the energy. And that's why we need to design mapping and filtering algorithms that fit processing in memory. So this is a new paradigm instead, or an alternative to the Neumann model, where you have the memory and the CPU separated from each other. Now you try to do the processing next to where the data is stored. And this is what we call FPGA-based NearMemory Acceleration of SneakySnake. So our solution is to perform read mapping near where data resides, and we carefully redesign the accelerated logic of SneakySnake to exploit near-memory computation. So that is a capability or a nice feature provided by Xilinx in their board, their recent board, which is, this is the board number. So you can go with ultra scale boards. Most of them, they have this high bandwidth memory or HBM. So that is located next to the FPGA logic board. So you have the chip located not within the same, either in the same package or very next to it. So it's different from 3D stacked memories, but these memories have very high bandwidth where you can fetch a huge amount of data with the less latency to the FPGA logic to do the computation. So we do the comparison with another one that use traditional memories, DDR4, and we use Power 9 IPM station to do the connection. So now when we observe the speed up, there is a huge speed up over there because you have now higher memory bandwidth. Then you can fetch more data, then you can use more replications, and this is the number of replications you can have. And if you see compared to the CPU, we use 64 CPU threads over there, the dashed line, and this is the performance using the FPGA with the HBM. So the best performing is with the red plot, because or the green plot. It can scale very well. And use the connection of OCAPI or this framework to transfer the data from the HBM to the FPGA. Now with the energy saving, you can see the energy efficiency is almost 0, which means it's really high. So this is compared to the 64 threads using Power 9 machine. So the energy is really very high for these devices. And using the FPGA with the HBM memory, you can see the energy efficiency by reducing the data movement and make everything local within the same device. So you can see the saving. It's really very high, can be up to 2 orders of magnitude. So near-memory pre-alignment filtering improves performance and energy efficiency by 27x and 133x respectively over 16 core, that is 64 hardware threads, IPM Power 9 CPU. So the performance can be increased by order of magnitude and the energy by 2 orders of magnitude over a CPU implementation. Of course, if we compare it to DDR4 based devices, the numbers are much less, but the energy benefits will be high, still up to orders of magnitude. These are the things that you can do with SneakySnake. So we have now GPU, FPGA, CPU. We have also the near-memory FPGA acceleration. But we still, for example, lacking any implementation for UpMem devices, for example, or something around these emerging technologies or the new real PEM devices. Recently, we got these chips from Nvidia. I'm not sure if they're still available in the market or not yet, but this is very recent release of H100 GPUs. And these GPUs, they have a dedicated core to build the dynamic programming matrix, to do the sequence alignment on the H100 GPUs. And they claim about 7x improvement in dynamic programming calculation over the A100 GPU, which is the best exists in the market. We expect, once we have specialized devices, as in this, to reduce the bottleneck or to alleviate the problem with the sequence alignment. But still, I believe, even if we have dedicated hardware to do the calculation, normally using a cheap filtering would always be beneficial here, because if you can implement the dynamic programming in specialized hardware, I'm sure you can leverage the same hardware to do filtering while reducing the computation a bit. So this is to be investigated. Someone need to do evaluation or benchmarking with some of the filters on the same GPU and compare it to the dynamic programming performance. So Joel said it's going to be released in the third quarter of this year. Yeah, hopefully we get it soon. Then we start to do some evaluation in our group, doing some designs for new filters and new genome analysis applications. As I said, there are UpMem devices that are real PEM DRAM modules. So you have, similar to the DDR4 you have, for example, you have the memory banks, and you have the DPUs, the processing elements that you can do processing near the data. So it will be interesting if someone can evaluate SneakySnake, for example, in these kind of devices. All right. As the last slide, the key conclusion here, as we always say, most speed up comes from parallelism enabled by both novel architectures and new algorithms. So you always want to have an algorithm that is aware about the hardware you are using. You also want to use the hardware that can fit, or the best fit for the algorithm that you design. As we always show some examples on this. These are the pointers to study if you are curious about all these topics. Remember, we have 2 genomics courses. They are already public online from the previous semester, and you can also watch the lectures from this semester as well. That's it for today. If you have any question, we can take them now. Otherwise, we can end the lecture. I'm not sure if we have any question on YouTube. Yeah, if not, we can end the lecture.